These are the notes for LT4 in the energy unit. LT4, the primary difference between this one and then LT3, where we're looking at potential and kinetic energy transformations. Now we're actually calculating changes in energy. So instead of just saying one goes up, the other goes down, with that inverse style relationship, we're using the formula. So calculate changes in potential and kinetic energy. Mechanical systems, remember mechanical just means there's moving parts, using respective formulas. So using the formula for either potential or kinetic energy. So if you're in class, you know I made a suggestion that you also write these formulas on your formula sheet in that format. Remember, anytime you use gravity, we do not square the 10. Just Earth's gravity is an acceleration. That's why it's s squared. So that's not, I'm not crossing that off because it's inaccurate. I just crossed it off to remember that you don't square the 10. We just substitute a straight 10 here if we are on Earth. So notes are a little different for this target because of the fact that it's all calculations. So really what we're going to look at is putting these practice problems. Okay, we're going to work through them. I'm going to put a couple examples in the notebook, but then I'm just going to work through these. Okay, so it's a front and a back. Hopefully you have it. If not, hopefully you'll just be able to see it and follow along as we go through this. One of the things I'd like you to think about, and hopefully you'll kind of come to a conclusion by the end of this, is what makes it harder to stop an object. If you've got an object rolling down a hill, and you've got to stop it, you're at the bottom and you've got to slow this thing down. Would it be harder to stop an object because of its mass or because of how fast it's going? Because one of those is more important than the other one. Of course they both factor in. They both factor into momentum. So that gives an object its momentum. But think kinetic energy. Okay, we've played around with that a little bit. What is really, really important, and actually it counts as a factor of twice. So it counts twice in that kinetic energy formula. Is it mass or is it velocity? All right. So we've already talked about, when we talk about kinetic energy, okay, that's the energy of motion. Okay, so energy of motion. And we've talked about the formula. We've used it. Remember, it's half the mass, and velocity is squared. It's really important you know how to square something on a calculator and take the square root of something on a calculator. So you'll need to have one of those handy. When we talk potential energy, remember what we should say is gravitational potential energy. For whatever reason, when physicists are talking potential kinetic, they don't call it GPE, but we know that this is gravitational potential energy. And so this is due to position above, when I say above the ground, I guess it technically could be above the water, but like above a base level. So due to position above. Earth's gravity, okay, sometimes you may be on the moon where gravity is a third of that or whatever, but in this case, in most cases we deal with, this is where the 10 comes from, because every second an object falls on Earth or towards the Earth, it'll go 10 meters per second faster every second. And the formula for potential energy is mass times gravity times height. So this is where that 10 feeds in. Hopefully we know by now the unit for energy is a joule. Okay, so for any type of energy we figure out it's a joule. And conceptually, that's about it. Here's the distinction between the two. Now we just need to be able to use the formulas in this target. So, I'm going to put some on this sheet and then some in the notebook. And we'll start out with number 1. Number 1 says, what is the kinetic energy of a 10 kilogram watermelon? Kilograms. You've got to know that's mass. It's rolling downhill at a velocity of 3 meters per second. Meters per second. You need to recognize that as being a velocity by now. We're looking for kinetic energy. All right, so I'm going to put number 1 in here. We have a mass of 10 kilograms. We have a velocity of 3 meters per second. And we are looking for kinetic energy. So we know that kinetic energy is equal to half the mass half of 10, and the velocity is squared. Order of operations says we need to deal with these exponents first. To square something on our calculators, we're going to go 3, caret. Caret is that little guy. 3 caret 2. I just like to hit enter. I could have put that all in parentheses, that would be fine, and run it all together. I just like to square it, hit enter, and then we multiply it by 10 and multiply it by 1/2 is fine if you put it in parentheses. I just put in 0.5 because we know the half is 0.5. So our kinetic energy is 45 joules. So some of these are very, very simple, straightforward. Number 2, we have an example here where we have a 1,000 kilogram car. Here's our mass. This time, 3,000 joules, that's energy. That's kinetic energy because it's moving. We're looking for a velocity now. So V is going to be our question mark. Okay, V is our question mark. So I'm going to put this into our notebooks. So number 2, mass is 1,000 kilograms. The car has a kinetic energy of 3,000 joules. We are looking for velocity. So when we go to this formula now, right up here, we have 3,000 on the left. That's our kinetic energy. Half is still in there. The mass is 1,000. And we are looking for V squared. Now we can't do anything with the exponent yet. Okay, we're going to end up having to take a square root here at the end. So instead now we multiply out. So we have 3,000. Half of 1,000 is 500 V squared. Order of operations, after we multiply, now we divide. So 500 V squared divided by 500. 3,000 then divided by 500. I think is 6, but I don't want to mess that up. Alright, so 6 equals V squared. It's kind of like when you have a multiply, to solve for it, you do the opposite, which is divide. So if we have a variable that is being squared, to solve for just the variable alone, the opposite of squaring something is to take the square root of it. So now we take the square root of V squared, which is going to be V. We need to take the square root of 6. Square root, second key, top left. Where it says x squared, that's the button you hit, because you can see in a real light color, that gives you the square root symbol. So second, x squared. If you've got that on your calculator screen, you've done it correctly. You type in 6, enter. If we round to the 10th, it's going to be 2.4. So the velocity is 2.4 meters per second of that car. Okay, 2.4 meters per second. Number 3, I'm going to write it on here because we do this exactly the same way. We have the kinetic energy. Here's the mass. We're looking for velocity. So I'm not going to put this one in the notebook. So 7,000 is our kinetic energy. It's equal to half the mass, V squared. 7,000. Half of 1,500 is 750 V squared. We divide by 750, divide by 750, and so 7,000 divided by 750 gives us 9.333. So I'm going to carry this over here. So we have 9.3 repeating equals V squared. And so now we need to take the square root of that. So square root of V squared is V. Now, there's an easy way of doing this. Instead of clearing that out, second, square root again, so that's not different. But remember, there's a way to recall that stored answer. So we hit second, and then the negative key, the secondary function of that is ANS, which is answer, gives us then a final velocity. If we round this, because 5 says we need to round that up, 3.1 meters per second is the velocity, 3.1 meters per second. Switching gears a little bit, 4, 5, and 6 talk about potential energy. So we have a mass of 15 kilograms. We have 5 meters. That's going to be our height. That's the height above. And our potential energy is what we're looking for. I'll place this one into our notebooks. And I'm going to have to kind of squeeze it all on one side here. So we're looking for potential energy. The mass is 15 kilograms. And now we have a height of 5 meters. Our formula, mass times gravity times height. So I'm going to put it right here. 15. Gravity is always 10. I'm not going to state that in the problem. You just need to look at your formula. It's on Earth, so it's always 10. And then our height is 5. So 15 multiplied by 10 multiplied by 5. Answer is 750 joules. Number 5. I'm not going to place this one into the notebook. It's the exact same type of problem. Looking for potential energy. We have a mass of 3. We have a height of 10. It's up on a shelf. Potential energy is mass, gravity, can't forget the 10 from Earth's gravity, and then our height is also 10. So 3 times 10 is 30. 30 multiplied by 10. Potential energy, 300 joules. Number 6, same type of problem. We have a 4,000 kilogram elephant. It's sitting on top of a palm tree that's 25 meters high. No idea how it got up there. And we are looking for potential energy. Potential energy equals mass, gravity, height. So essentially we have 250 multiplied by 4,000. Answer is, let me get this right, 1 million. It's a massive elephant. 1 million joules of potential energy. You would not want the elephant coming down on us. Don't walk under that tree. Then, last one. On the back. This is perhaps the problem that confuses the most, this type of problem. This should look familiar from our pendulum gizmo. And this is a screenshot of this pendulum when it's swinging down towards the ground. Remember, we have a mass. We have a meters, but that's the length of the pendulum. That doesn't have anything to do with height. We have potential energy, we have kinetic energy, we have total energy. But this problem wants you to find the velocity of the pendulum. And what we have to remember is that potential energy, there is nothing about velocity in that formula. So that potential energy is no good to us. But kinetic energy does have velocity in the formula. So that's the one we're going to use. So we see that then, the mass is 1 kilogram. Okay, so it's going to be half, whoops, let me slide this up, sorry about that. Half of 1 kilogram. There. And then the velocity is squared, that's what we're looking for. And our kinetic energy value comes from up here, and I know that's very small, but that's a 1.5. So we have 1.5 equals 1/2 multiplied by 1 multiplied by v squared. Half of 1 is 0.5. So now we divide each side by 0.5. Those of you that wouldn't want to do that in your head, it should be 3. So we have 3 equals v squared. Now we want v, so we're going to take the square root of both sides. And the square root of 3, we can go second square root. Recall that 3. So second answer to recall the 3. And that means that pendulum would be swinging at 1.7 meters per second. Okay, 1.7 liters per second. Now, just to go back to that opening question, what makes it harder to stop an object? Its mass or its velocity? Hopefully, after using these formulas, you can see mass only counts once in either of these. But think about that velocity. That's squared. So if something's actually going 3 times faster, 3 multiplied by 3 squared is 9, it's 9 times harder to change its energy. Okay, 9 times harder. So the conclusion to this question is it's actually velocity that factors in more if we're trying to stop an object. Those of you that are in sports, one of the arguments just from a softball, baseball perspective is bat speed. So is it better to swing a heavy bat and not have bat speed, or at least as much, or a lighter bat and get a lot of bat speed? It obviously pays to be able to do both, but you never want to sacrifice the bat speed for an extra ounce or 2 on that bat because of that kinetic energy formula. All right, so there's actually a lot of physics involved. All right, good luck.